So today we have the pleasure of having a talk by Ivailo Hartarsky from Technische Universität Wien, and he's going to tell us about why bootstrap percolation is local. Ivailo, you have the floor.
Okay, thanks. So it's a really great pleasure to give this seminar to talk about this precisely at this seminar, because this is joint work with Augusto that we started 2 years ago in IMPA and then continued in Lisbon and a number of other places. So I'm very happy to talk about this. So let me start by defining what the model we're going to talk about is. It's called Froboese bootstrap percolation. And it works on the square lattice where each site is either healthy or infected. And I'll draw this as white or black. So I have a configuration like this. And this is a cellular automaton that performs the following rule. Whenever you see a 4 cycle with 3 black and 1 white, the white will become black. And other than that, nothing will change. Okay, so let's see what this gives on this initial condition. On the first step, I get these 5 sites infected because each of them is in a 4 cycle. Then I iterate this. So these become black, and then I repeat, and I get these 2 new guys, and so on and so forth. Now you notice that this square at the top is already kind of stuck, while the thing at the bottom is growing to make a rectangle. But it keeps growing, and now it's trying to form a bigger rectangle here, but it eventually meets the square at the top, and they merge to form, to eventually infect everything. Okay, so this model was introduced in the 80s in statistical physics. It has links to various things like metastability, the stochastic Ising model at low temperature, kinetically constrained models of supercooled liquids, and many others. So you can take the statistical physics viewpoint on this, which is what we will do. But before I get there, let me mention a few combinatorial things that you may want to look at for this model, which are very natural. So particularly for those of you who know everything about this, I will give a few exercises. So the first one is the following. If you take an n by n square, how many black sites do you need to put to make it all black? So this is an extremal combinatorial question that there's no probability in it. Another natural one that you could ask is how many steps could it take before you become stationary? So, okay, you keep adding infections and eventually there's nothing else to be added. Again, on the n by n grid. So these 2 are really very nice exercises. I highly recommend if you're bored. The next one is a bit harder, which is of enumerative combinatorial nature. So if you already managed to solve exercise 1 and found the minimal number that you need, you can ask how many configurations there are with this many black sites that get the n by n square black. Okay, so this I'm cheating a bit. It's a bit of a hard exercise like this, but hopefully by the end of the talk you will have more or less the tools to do it. Okay, but we're not going to do combinatorics. We will be doing statistical physics. So what are we going to look at? A natural observable to look at is the infection time of the origin when you work on the infinite square lattice. And so far everything is deterministic. To add some probability, we will take the initial condition at random with with parameter p. Every site is infected initially independently of everyone else. So it's the product Bernoulli measure. And to fix ideas, I want you to think about p small, which is the physically relevant regime of low temperatures. So we will see in a second why this is the interesting regime to look at. Okay, so if the model is not clear, this is a good time to stop me. Otherwise, I can keep going. So a few results on this model. The first one is the first rigorous one by Van Enter tells you that for any positive value of p, almost surely the origin will become infected at some point. And this is why, so this is a trivial phase transition, and this is the reason why we like to look at p going to 0. because then you expect that it will take longer and longer to infect the origin, and you want to know the asymptotic behavior of this random variable. Now, the first quantitative result is due to Eisenman and Lebowitz, who showed that this infection time is exponential in 1 over p, bounded between two different constants here. And I can actually tell you, and this is all as p goes to 0. I can actually tell you how this is proved. For the lower bound, they use what we call the rectangles process, which is another way to determine what will become infected when you run the dynamics, but not by running the dynamics. So how does it proceed? You start by surrounding each infection by a little square, and then whenever you see two squares that touch along a side or intersect, you merge them and replace them by a bigger rectangle that is the smallest rectangle that contains both. Okay, so let's see what we can do. For example, we can merge these two, but you can do this in any order you like, it doesn't matter. Then I can look here and see that I can merge these two, for example, then these two. You see this rectangle plus this square gives me this rectangle that is the smallest one that contains. And you keep going like this. Now this guy here is stuck, but here I can keep doing things, so I can do that. And now I can merge these two. And now this one is contained in the big one, so I can just remove it. Okay, so this is a way to see that everything will become infected in this square if you start with this initial condition. And okay, so I won't go into details on the lower bound, but this is really the only interesting ingredient that goes into proving the lower bound. Once you have it, it's really not hard. Now the upper bound uses a different kind of mechanism, which is based on what we call a critical droplet. So this you can think of as a sufficiently large region that you somehow manage to get infected. Now, I will give you one way to obtain such a region, which is the following. Assume that you have an infection here and an infection here. Then if you have at least one of these two infected, the other one will also become infected for free. And if you have at least one of these two, you get the other one. If you have at least one of these three, you get the other two. If you have at least one of these three, you get the other two, and so on and so forth. Okay, so if all of this happens all the way to infinity, I get a quarter of a plane, and okay, this is basically all. So how big is the probability of this event happening all the way to infinity? Let's see. I ask for one infection, one out of two infections twice, one out of three infections twice, and so on. So the probability is exactly this. And when you see this, the first thing you want to do is to write it as an exponential of a sum, probably, and maybe use a little bit of convexity to make an exponential. That's all I used here. And when you see this, you suddenly want to compare this sum to, well, it's a Riemann series, so you want to compare it to an integral. And if you do that, you get this. If you see this integral, you probably want to change variables and call this y, and then you get this. If you see this integral, you probably want to expand this as a Taylor series, the log, and maybe use a little bit of Fubini to get here. And now even I am able to do this integral. And when you do that, you get the zeta function. So in the end, the probability of our event, and these inequalities are very close to being equalities, so you should really think that it's basically exponential minus pi squared over 3p when p. Okay, so this is the probability of this event happening all the way to infinity. Now, I don't need it to go all the way to infinity. I can truncate it at a certain well-chosen big size, but it doesn't need to be chosen very carefully. And the probability is still basically the same. Okay, so now the question is, how far from the origin will I see an instance of this truncated event, a translate event? And the answer in 2 dimensions is, well, exponential pi squared over 6p, where the factor 2 is because of dimension. Okay, and once I find this big square, it gets completely infected very fast. And if it's big enough, it's very likely that it will grow at approximately linear speed until it reaches the origin. And so what matters is really the distance, which is exponential pi squared over 6p. So when you put this argument together, you get exactly the Eisenman-Leibowitz upper bound with pi squared over 6. And I didn't hide anything here. All right, now quite a bit later came a breakthrough of Holroyd, who proved that this pi squared over 6 is the correct constant. And I should mention, in this business, proving lower bounds is much more difficult generally than proving upper bounds. So he needed to introduce a large number of important techniques to be able to prove this that I will not describe. All right, now once you have this, it's natural to go and look at the error term here. We will see a bit later why this is an important thing to do, but for now you can just wonder. So this was first done by Grabner and Holroyd, who showed that this error term is big, in the sense that you have this exponential pi squared over 6p, but in front of that you have at least a stretched exponential correction. So quite big. And the lower bound was proved by Grabner and Holroyd, again, up to this polylog matching the same power. But for a slightly different model, which I will call the local Froboese-Bootstrap percolation. I will define that formally on the next slide, but for now you should just think of it as a slightly simpler version of the model. And the reason why I don't want to define it now is that 3 years later, together with Rob Morris, they proved the same thing for the original. Now this was improved, the power of the polylog was improved by Brinkman and Malberg to 5/2 back to the local model. And quite a bit later with Rob Morris, we proved for the non-local model bound without logs. But for a slightly different but very closely related. Sorry?
I have a very stupid question.
Go ahead.
So there is a 6 that became 18, but maybe the model changed in between, or
the model changed, yes.
Okay, but this one seems to be the original model. There is no log here.
So there is no log in either of them. So the only place where I changed model is here, and this 6 became an 18.
Okay. So this is this is not Froboese, neither local Froboese.
Yes. It's slightly different. You should think of it as a bit more difficult than the original Froboese model.
Okay. Thank you.
No, thanks. Yeah. All right. So that's anything else? Okay. So I promised I would define the local Froboese-Bootstrap percolation, so that's what I'm going to do now. This is a 3-state cellular automaton now, which has healthy, infected, and germed. And germed is the worst. So I'll go slowly. If you only have healthy and germed, this is exactly the model that you already know, the Froboese-Bootstrap. So if you have a 4-cycle with 3 germs and 1 healthy, it becomes a germ. So far, so good. Now, the role of infections is that they will more easily be invaded by germs. So if I have an infection and a germ next to it, it will become germed only by 1 germ. All right, so let's see what this gives on an example. To be sure, I have only 1 germ, and so other than these 2 rules, nothing happens. So if there are no germs, nothing happens. So here, only things can happen around germs. So on the first step, by the second rule, I will get these 2 guys germed. And for the same reason, on the second step, I will get this guy. But I will also use the first rule to get a germ here. because of this 4th cycle. Okay, and then for the same reason I get this one. And then it's stuck. All right. Now, on the other hand, you can see that if these infections were germs instead, this would infect, would make everything germed. So this is somehow, if you have the same set of infections in the original model and here, but you make some of those infections germed, then this is less contagious than the original. If you make all of them germs, then it's exactly the same as the original. All right, now what we will do, we'll take exactly the same initial condition as before, product Bernoulli. These will be the infections. And okay, if I don't do anything, this doesn't do anything. So I will need to add some germs. I will add only one germ. So I will transform one of the infections into a germ. If I do this in a stupid way, for example, if I make this lonely guy a germ, nothing will happen. So I give it a little bit of a chance. So I let you optimize over which infection you want to turn into the only initial germ. Okay, I hope this was clear. Let me repeat. You start with product Bernoulli infections. One of them you turn into a germ. You choose which one. You compute what is the time when the origin will become a germ, depending on which infection you turn into a germ, and then you optimize over this choice. All right, so I hope it's clear. Based on what I already said, it should be clear that this local infection time is bigger than the original infection. All right. This model is less contagious. So the question is how much bigger? Now I should mention the way to think about this local verbose model is that it's a slightly simpler version of the model because it only allows you to grow from one place rather than from several places, and then they interact and they merge and do crazy stuff. Okay, so this is why it's somehow simpler. And this is why you are able to do more for this. Okay, I hope the model is clear. You can stop me if not. Otherwise, I can tell you already what our main results with Augusto are, starting with what I call the locality theorem, which tells you that, in fact, these two models are very close. Namely, the ratio between these two things, which we know that is at least one, is at most exponential of polylog. And this 19 we did not optimize, of course. Okay, so to convince you that this is useful, I will go back to the previous results. So it's useful because, for example, it tells us that this paper is equivalent to this paper. Right? They only differ by this tau and tau log. And actually, in this entire slide, always the bounds we are proving, the error terms we are leaving are much, much bigger than the error term we have in the locality theorem. Okay, so the way you interpret this result is that you can completely forget about the non-local model. You can just study the local and you are good. And this is very good news because
I'm sorry.
Yeah.
I'm sorry. Can I ask a quick?
Yeah.
I didn't understand how you chose the. It's a little bit how you chose the star. Can you repeat,
Right.
please?
Sorry. Right. Yeah. No. Thanks. So you start with product Bernoulli infections, and you are only going to turn one of them into a star.
Mm-hmm.
Okay, so a priori it could be any one of them. For each possible choice, you get a certain time when the origin will become germed. And then you minimize this result over the possible choices of the initial star.
Okay, so you just take the worst one.
Yeah, well, worst or best, I don't know.
Okay. Thank you.
Thanks. Okay, so the use of this result is that you reduce the study to the local model, and the local model is much better because for it proving lower bounds is now much easier in the sense that it's about as hard as proving upper bounds. This is really great news. It's completely not as it used to be with Holroyd's result, for example. Okay, so thanks to this, we were able to go much further. So we studied the local model and proved quite a bit more for it. Namely, we determined the exact constant to put in the second term, and we even bounded the next order term. Moreover, and of course, when you put these two things together, you get the same asymptotics without the local. Right, now, this actually applies also for, to go back to Hubert's question, to the more commonly considered two-neighbor bootstrap percolation model, for which you have a different constant, it's pi square over 18 instead of pi square over 6, and this pi root 2 plus root 2 changes to something else. But basically the entire proofs work, they're just a bit more technical for this. And this is the model that we were working on with Rob. All right. Now, before I tell you anything about the proofs, I want to do one more thing, namely convince you that you might have a reason to care about the second and third order terms and so on. It's not just because we're curious, it actually is a meaningful thing to look at. So to explain this, I will need to tell you a bit about what we call the bootstrap percolation paradox. This is the following. The most natural thing you would like to do when you see this model, it's a cellular automaton, so it's basically made to be simulated. So what you would like to do is to just fix your value of P, take a random initial condition, find the infection time, do this a bunch of times, gather the statistics, maybe take the average, and plot this against P to then infer this kind of asymptotics. Okay, simple. So you do this for a quarter, 1/8, 1/16, and so on. And this is what you do. Now the problem with this is that I already cheated. And the place I cheated you is that you can't even reach values of P as small as 1/16 by doing this. So the biggest simulations that have been done only stay here. And the reason for this is that already at these values of P, the typical values of the infection time are maybe a few 100,000. And if you want to simulate a few 100,000 by a few 100,000 box, it takes time. Okay, so with this kind of Monte Carlo approach, you can't get very far. Okay, based on this, it's actually not clear what you should do. Here I plotted it in terms of log 1/p, but maybe you would like to plot it in terms of 1/p or p, in which case you would get something that seems to would get much flatter here. You might think that it converges to 0.8 or something like that. If you plot it in terms of log 1/p, it looks perfectly straight to me. So okay, it's not clear. Now we know some things from Eisenman-Lebowitz. We know that this thing that I'm plotting is going to be bounded from above and from below. Okay, so it's probably going to converge to something. And you need to figure out to what. Okay, based on this, you might guess 0.8, which is not a good idea. But we also know from Holroyd that the limit is actually here. So very far from anything you get even for huge systems. So this was actually quite a surprise when it came out. And so people wanted to understand what's going on. So about 2 decades ago, Di Gregorio, Lawler, Bradley, and Dowson suggested looking at the local model to figure this out. And the advantage of that is that you don't need to do a Monte Carlo simulation for the local model. You can do something smarter, which I will explain a bit later in detail, but using some exact computations of some probabilities, you can get much further without doing a Monte Carlo simulation. And they went all the way up to physically relevant scales for material science, like Avogadro number. And based on this, then, okay, you see that it's going towards the right value, but it's still pretty far. So you might think that there is a corrective term, which is probably a power law, because what else could it be? And you can try to estimate what's the power of this power law, and that's what they did. And the surprising thing is that what they got was a wrong exponent for this second order term. This is what Grabner and Holroyd were proving. The exponent is a half, and what they got is, I think, something like 2/3. So this was quite a disappointment because they went all the way to crazily big sizes in principle. But together with Augusto, we didn't feel obliged to stop at physically relevant scales. So we went way past astronomical scales and got this. So now it's clear that it's going to the right value. I think this is obvious from the picture. But we can also compare it to the rigorous result with the second term that we proved. So here's what it looks like. Of course, you get, well, I don't know to what extent it's of course, but you get an extremely good fit around here and not so much of a good fit around here. Okay, so it's not so surprising that you didn't get the right asymptotics based on looking here. Okay, but based on this, we can actually play the same game physicists played. These points, we don't tell them about this asymptotic, so we can try to deduce it to see if it works. So you do the most straightforward thing, take the last 4 points, do a 4-parameter fit, AP to the alpha, BP to the beta. What the computer spits out is numbers, which are to be compared to the actual numbers. So you get an exponent which is basically 0, as it should be, a constant which is basically what it should be, a second exponent is not quite a half, but not so far, and then the next constant that's not quite what it should be. It's the same, the right order of magnitude, the right sign, but not quite. Okay, so pretty happy. Now the thing is, you can do something smarter. When you have this, you can probably guess that the first exponent is exactly 0. You can maybe guess or know the first constant. You can then improve this exponent, guess that maybe it's exactly a half. If you guess all of this and try to only figure out this constant, you get something very good. Okay, and of course the moral of this is that we are actually looking at the same thing, but we're getting there from infinity. So you can probably imagine that if you get a third order term, then things will start looking even better. All right. So I hope I motivated you that you might be interested in looking at these subsequent corrections. So let me go back to the result, and to motivate you one final bit, I will just try to tell you roughly what kind of things go into these results, because I won't have the time to tell you everything about the proof. So in the locality theorem, we use quite a number of things, including some combinatorics, some random walks, and some large deviations. While in the asymptotics here, you see several other things. You see pi squared over 6, which is eta of 2, okay. And this is actually not so innocent. Number theorists were interested in these models and generalizations because of the links that they have with some integer partitions with constraints. And this is quite related to that. Now, if you look at the second order term, this pi will come from some optimization problem on some differential form. This root 2 plus root 2 will come from some perturbation of matrix spectrum. And if you want to look at the next order term, you need to also start doing some stochastic analysis. So I find it quite fascinating you have all this in such a simple looking model. And okay, so that's what I want to say about the results. I hope you are sufficiently motivated to listen a little bit about the proofs. Now I will only give you some impressions of the proofs, just to have an idea of what kind of arguments you might want to use and where the various constants come from. But it's also a good point to ask questions if you have any. All right, so I'll start with the locality theorem. So for locality, I need a definition. I called it a rectangle internally filled if the black inside is enough to make it completely black. Okay, it sounds like a reasonable notion. And if you remember the rectangles process that I described, the next lemma will not surprise you. It says that the rectangle is internally filled if and only if there exists a decomposition into two rectangles, like in the picture, which are internally filled, disjointly occurring, if you know what that means. And when you merge them in the rectangles process, they give you as a result, R. Okay, this really follows directly from the rectangles process. So what do we do with this? There are some decompositions that we like if we are trying to prove locality. Locality is comparing the non-local model to the local. So some decompositions we like because they are in both. We call these local decompositions, and they correspond to one of the rectangles being a single infection. So if you imagine that S is completely germed and T is a single infection next to it, then I would indeed manage to get all of R germed. Good, but there are also some decompositions that we don't like, the non-local ones. If S and T are both kind of big, then this corresponds precisely to the thing I don't want, namely both things growing and then merging. So this I don't want. How do I deal with that? Depending on the situation, we want to do one of two things. The first one is compute such a ratio. So the probability of getting S internally completely infected from the inside, getting T internally filled, to getting R locally internally filled. So in the local for both of those. So how do we go about proving that such a thing is very small? We need a priori bounds on both probabilities that appear here. The good thing is that we don't need very precise bounds. We only need, well, rough bounds. And we can hope with rough bounds to get that the model is local, and then once we know it's local, we can get much better bounds, which we could in principle also bootstrap, but we don't need it. Here we managed to get there in one go. So this is one possible strategy. The other possible strategy, and we need both, is to keep S, but compare the probability of internally filling T to the probability of S growing to give you R in a local way. Okay, so here again you need some a priori bounds on the two things, okay, then you can hope to get them. Now, as I said, depending on the situation, what do I mean? There are a number of cases that we need to consider, which can look like this. I won't go through all of them, don't worry. I'll just give you an idea of this one, and I will further assume that S is a square. We have a square and a small rectangle next to it. Why is this not a good idea? Well, let's compute the two probabilities, and what I will be trying to do is this kind of bound. So I want to compute these two probabilities roughly. So the denominator is easy. I want S to grow to give me the result of merging S and T. To do that, it suffices to have an infection on each column here and each row here. And as a result, what's the probability of that? Well, it's at least this thing, because there are S plus T minus 1 rows and columns in total at most, and each of them is at least size C. Okay, so easy. And if C is not very small, sorry, not very big, you get this kind of approximation. Okay, so this is one of the bounds. You see, it's very simple a priori bound. For the other one, it's a little bit more difficult, but I will hope that you already solved your exercises and will not be surprised by this lemma. So we prove for any rectangle T, which is S by T, you can prove this a priori upper bound on internally. It's not particularly sharp, but it works. So you can see that if, well, if you believe me, it's true, and you compare these two things, if C is at least twice S, then you are happy. Okay, now I will not explain how you prove this, because to prove this you first need to solve your first exercise and then think a little bit about the third exercise. But once you have done that, it's really not such a big deal. I just wanted to give you an idea of what these a priori bounds that we prove look like. We actually need multiple, and this is one of the simplest ones, but this is the kind of argument that we use. Okay. So this is everything I want to say about locality. Once you have it, you only think about the local model. What do you do with it? So why is it so much easier to work with the local? To explain this, I will tell you a little bit about how we get these points in this plot, these black and red points for the local. So for the local model, you can do the following kind of exploration based on the rectangles process. You imagine you have somehow managed to germ this rectangle here. It's a square, by the way. Then you try to extend it to the right. There are two options. Either you manage or you don't manage. Let's say you don't manage, so there are no infections here. You keep that information and you try to grow up. Maybe you manage. Okay, very good. You try it again. Maybe you fail this time. You keep going like this. Okay, so all of these transitions, you can compute the probability explicitly. So they correspond to like 1 minus p to some power, or 1 minus 1 minus p to some power. You can write it down, and it's very, very simple. Okay, so based on this, you can compute the probability of reaching a certain rectangle of a certain width and height, and with certain what I call frame state. So whether these buffers which have no infection inside are there or not. Okay, there's only finitely many frame states. So you can do this. You can compute this exactly by dynamical programming. You just keep increasing the perimeter. And you compute this recursive until you reach a certain sufficiently big size. And once you're there, it will for free grow to infinity, and then you're happy. So what you want to compute is the probability of reaching that, and this you can do by induction numerically. So this is actually quite efficient. It's only quadratic in time, and it's even linear in space, which is very good. Moreover, you can actually take advantage of the fact that you can do many things in parallel. Typically, you can do a computation here and a computation here at the same time. So this allowed us to reach such very small values of p or very large system sizes. Of course, when you do this, you need to be a bit careful, because the probabilities you're working with become very, very small. Like exponential of 2 to the 17 with a minus somewhere. So really not something you want to work with directly. You need to be a bit careful to simultaneously be efficient and have precision. So we did this, but I don't think this is what you want to hear about. At any rate, this is how we get the data. And the reason why I wanted to explain this is that it's actually useful for the proof. So the proof of the upper bounds goes along these lines. We consider this framed rectangle Markov chain, which looks like this. Let's say you start here with, you don't know anything about what's around you, you want to grow to the right. If you find an infection, you grow, but you still don't know anything about what's around you. And okay, this corresponds to this loop. Otherwise, you may find a buffer, and then you transition to this state. At this point, you can again do a loop, you can get blocked, or you could find an infection on this line and find an infection at the corner. If you find both of those, then you will destroy this buffer, you will get a rectangle that's a bit higher and a bit wider, and you will not know anything about what's around. So you get back here. Okay, so you keep going like this, you figure out what this graph is, and it gives you this. If I look at this from a little bit far, and I forget this this absorbing state that I don't want to visit, I will get this picture. You can look on the left or on the right depending on your background, but independently of your background, I'm sure that you all know by heart the spectrum of this matrix or graph and know that it is this. So this root 2 plus root 2 is the one that will come up in the final answer. Okay, so far so good. Let me tell you something about let me tell you something about the lower bounds. So as I said, somewhat surprisingly, it's no longer much more difficult. It's more or less the same kind of stuff. So we have our frame rectangle Markov chain. Now, I should confess I lied to you. It doesn't look like this. It looks a little bit more like this. But okay, it's not that bad. It looks more like this, for example, because if you're here, you find an infection here, you find an infection here, and at the same time you find an infection in this corner, then you will destroy two buffers at the same time, and you will go back here. But okay, it's not that bad, you can figure it out. Another thing I lied about is that so the graph doesn't really look like this. It's not zeros and ones, they have weights. But okay, it's not that bad. So what does it look like? It looks like this. And when I add these additional things, it looks more like this. So it's some matrix, which was nice. Now we perturbed it. Now the perturbation is a little bit nasty because it's bigger than the matrix. But also the matrix is a bit ill-conditioned. It's really not that nice, but it's okay. You can compute we don't compute the spectrum explicitly, but you can show that the perturbed spectrum is pretty close to the spectrum that you started with. Okay, so that's good enough. Now, one thing I did not tell you about is where this pi comes from, and this is the last thing I want to explain. So this, the pi in the second order. So to see the pi, you need to look at trajectories of this kind of chain, but when you keep track also of the width and height. Okay, so what happens if you do that? You get a diagram like this with the width and the height. And you have these blue transitions that correspond to loops in the previous picture. So those correspond to trying to grow and succeeding. Okay, so what's the probability of these things? Only imagine there's blue things for now. So I will need this function that you already met in the Eisenman and Lebowitz proof. And I will need a little bit of notation that you can, you can completely replace Q by P, but it will make my notations. Okay, so what's the probability of this transition here from a rectangle A times B to a rectangle A plus 1 times B? I just need to find one out of B infections, which I can rewrite with this notation as exponential minus f of B cubed. All right, now notice that the cost of growing width depends on the height, and the cost of growing in height depends on the width. Okay, so an observation. When you multiply this stuff along this path for all the blue transitions, you get this kind of differential form with this f of y dx plus f of x dy, because width depends on height and vice versa. Now this differential form is optimized along the diagonal. This is you can prove it's due to some convexity. And okay, what is if you are along the diagonal, then you get integral of f of x dx, and the integral of this function f from 0 to infinity is pi squared over 6. But this is what tells you where the first order term comes from. Now we want to see where the second order term comes from. So you need to look a bit more refined than that. So the second order term will come from the other transitions, these green and orange. So I want you to focus on green and orange, and I will even assume that I have a green and then immediately an orange after. All right, so what's the probability of this kind of thing? I have this rectangle. I fail to find an infection here, and then I find an infection here and an infection here to destroy this bubble. What's the probability of that? It's just this. And with my fancy notation with the F and the Q, this you can write like this. So this guy here is e to the minus bq, p is p, and this is e to the minus f of aq. Very good. And then I added and subtracted f of bq. So when you see this, why I did this addition and subtraction to make this thing appear, which starts looking like the differential form we started of this one. Right? So basically I'm replacing this orange by two blue transitions, or at least for what would have been two blue transitions. So this guy will just recover the blue path that I claimed I had before. But you have this rest here. What is this? Let's compute this function. It's 1 over e to the x minus 1. You can believe me on that. And one last thing to note is that you get a factor like this for every two transitions, a green and an orange. So you can imagine that you get root of this for every green or orange transition. Okay. So when you believe this, you already see a root p appearing. And what else you see is a root of this function appearing. And then it will not surprise you, perhaps, that the integral of this function is, well, pi, when you root it. So this is where the pi comes from these green and orange transitions, which actually happen quite rarely. And then, of course, you do some Riemann sum that you approximate by an integral, and you get this kind of. Now, of course, for the lower bounds, it's a little bit more complicated, in particular when you need to optimize your differential forms, because you need to take also into account the second term. But okay, we managed. All right, so let me conclude by talking a little bit about possible future directions. So for this model, this tells you basically everything or close to everything. But there's a lot of things that you can ask once you have this. So, okay, the first one, I might even, okay, this is more of a joke, I'll skip it. You can ask for subsequent terms in the asymptotics, which would require some stochastic analysis, as I mentioned. But what I find much more exciting, actually, is looking at different models. In particular, there is this modified two-neighbor bootstrap population that I can define if you are interested. It's a very similar model somehow, but which turns out to be much more complicated. In fact, Di Gregorio, Lawler, Bradley, and Dawson were looking precisely at that model because computations are slightly more convenient there. This was quite an unlucky choice because this model is more complicated for several reasons. The first one is that if you can play this game formally, you can compute the function that you would get here for that model, and it turns out to be non-integrable at 0. It actually has a logarithmic divergence. And this gives away the fact that there is, in the second order term, there is a logarithmic correction that you need to take into account. And this is actually what we believe made them conjecture a different exponent in the second term. Now, this is not the worst problem. This perhaps you can deal with, but a worse thing is the fact that locality does not hold as strongly as for the Frobosen model. In the sense that you will not have this exponential of polylog. In locality, it will be much worse. It will be stretched exponential. This is actually going to be, the two models are going to be significantly different in that. One final thing I would like to mention, which is interesting about this model, is that at very small scales, you see interesting patterns appearing. Well, if you solve your first exercise for this model, then what you see appearing is called separable permutations, which are well-studied objects. We know how to count them, we know scaling limits, and so on. And they appear naturally at low scales in this model. So to treat this, you would need to somehow mix all of this together, which I find quite challenging. Okay, and of course you can look at further generalizations for other models. Higher dimensions have not been looked at. It will also be interesting to look at local models even without knowing locality, also because you need a priori bounds on local models to prove locality. So it makes sense to look at them for their own. Okay, and finally, it would be very interesting to see if in such situations where locality doesn't hold that well, whether it's possible to obtain accurate asymptotics based on numerics. Okay, but that's everything I wanted to say. So thank you very much.
Thank you, Ivailo, for a very nice talk. So are there any questions? No questions? Okay, so if not, let us thank Ivailo again. And I don't know what the next sessions for the seminars are, but maybe this was the last one. Hubert, can you confirm?
Well, Hubert left because he had an exam.
Hubert went to his
exam.
Yeah, Hubert has the exam. Chiara, do you know if there are other sessions for the seminar?
The last one.
Yeah, this was the last one?
Before the break.
Yeah.
Okay. Well, so Ivailo, you had a prime spot. Okay, thank you everyone. Bye.
So then thanks to the organizers for the semester.
Bye.
Bye.